Hi students, hope you are doing well. Today I am going to start lecture 19 and today's lecture is about the lift drag pitching moment coefficients which play a very important role as far as aircraft are concerned. I am Dr. Ranjan Ganguly. Now before looking at these coefficients, let's review the basic concept about the forces and moments which act on the airfoil section. So if we consider an airfoil which is in a given flow, so there is a velocity v coming from the front and the angle alpha is there with the chord line of the airfoil section. Now what happens is that the forces which are going to be generated on the airfoil are the lift, the drag and the pitching moment. So the lift is L, this is normal to the velocity, the drag is D, this is parallel to the velocity and the pitching moment is at the quarter chord, which is also the location of the aerodynamic center in subsonic flow. So we are going to consider this L, D and M and look at non-dimensional measures for these three quantities which are going to be very useful as far as aerospace is concerned. So let's start with the mathematics. Now we know that the lift is going to be a measure or a function of several quantities. So these quantities would include velocity, density, the area of the wing, the viscosity mu and the speed of sound a. So these are essentially coming from our physical thinking about a situation. If you were to place any airfoil or wing in air, then you would naturally think that it's going to be a function of the density of air, the velocity at which the body is moving, the area of the body and so on. So lift would be a function of these quantities, and also from the fact we know about viscosity, because viscous flow is something which is a reality, and compressibility effects, typically they would also be a function of mu and a depending on the speed at which you are flying and so on. So we keep all these measures here and then we will try to get the functional relationship. So L is a function of these quantities. Now since we do not know this functional relationship, what we will assume as a very simple assumption is that it is a multiplicative relationship. So we say L is some value z into v infinity to the power a, rho infinity to the power b, s to the power d, a to the power e and mu to the power f. So here all these values z, a, b, d, e, f are non-dimensional numbers, and we don't use the value c here because we already have kept c for chord, so we don't want any confusion about that. Now once we consider this to be our formulation or functional relationship, what we are going to do is we are going to match the dimensions on both sides of this equation. So remember, the dimensions are expressed in terms of mass, time and length. So let's think in terms of unit. For example, lift is a force, so its unit is going to be in terms of Newton, or you could write it as mass divided by t square into L. So this is the dimension of lift. Similarly, we see velocity is meter per second, so it's here. Density is like kg per meter cube. Then S is simply meter square. A is meter per second, again it's the speed of sound, and mu we remember from the units of viscosity is kg meter second. So basically from our knowledge of units of these quantities we can easily write this relation out, and what this relation is going to help us do is that it's going to remove certain redundant indices which are there. So we are going to do that next. So what we do is now we write equations based on balancing the indices of each of these quantities. So let's look at mass first. So on the left hand side, mass has simply to the power 1 raised here, so it is 1, and here mass has to the power b, so we have b plus f. So that's the second one. So 1 equals b plus f if we match the powers of m on both sides. Similarly, we look at time. So time here is t squared, so it is minus 2, because if we take the t up it becomes t to the power minus 2. So that's the index here, and here one index is minus a, then you have one more index is minus e, and another index is minus f. So that comes in here, that's minus 2 is minus a minus e minus f. Now the third is about length, so here we take length has power 1, so there's 1 here. Here it's power a, so there is a, then there is power minus 3b, so that's here, so minus 3b, because if we take L to top it becomes L to the power minus 3, and then we take the b, so it becomes minus 3b. Similarly 2d and L to the power e, so e comes here, and L here is minus f because L goes up, L minus 1, and then f, so minus f here. So these three equations are going to help us remove some of these quantities. So now, right now we have A, B, D, E, F. So some are going to be removed. Now how we remove that is we are going to simplify this. So for example, if we have mass like this, I can write B in terms of F. So B would be 1 minus F. If I have time giving me this equation, then I can write A in terms of E and F. So A, if I take it to the left hand side, would be 2 minus E minus F, and then the third equation is going to give me the next quantity, but I have to do some math here. So let's start with the third equation here, and what I do here is that I substitute A and B from these two equations into the third equation. Okay, so I substitute A is this value here and so on, and so that's going to simplify things for me. So first I write this d out, so I write d is 1 minus f plus f minus a and so on, so whole thing divided by 2. Then I further expand this d out by putting in the values for a and b, and then I get some cancellations, and the cancellations finally give me d is 1 minus f by 2. So essentially what I have done is I have got rid of a, b and d, and so I can write this L only in terms of e and f, which you see here. So now what we have is we have this v infinity, which was the velocity, to the power a, and we know a is 2 minus e minus f, so we have that here. We have the next one, which is density, and density had power b, so that's 1 minus f, 1 minus f comes here. We had L squared to the power d, so I have s to the power 1 minus f by 2, because d is 1 minus f by 2, and then I had the speed of sound to the power e, and I had the viscosity to the power f. So this is now my new functional relationship of f, and so I have managed to remove some of the indices here. So now what I'm going to do is I'm going to take that equation which I wrote in the previous slide, and I'm going to simplify it further or write it in a different form. So let's say we pull out one by one the different quantities. So let's pull out rho infinity here. You see there is a rho infinity to the power 1. So I can bring that out here. I get rho infinity. There's a v infinity to the power 2. So that's this value here. And there is s to the power 1. So that's this value here. Then I get a, and I get v to the power c to the power e. So I get a infinity, or a infinity to the power e, that's this value, and then v infinity to the power minus e, so the v infinity goes down. And similarly I get mu infinity here, I get rho infinity minus f, which comes here, I get v infinity minus f, which comes here, and I get s minus f by 2, which comes here. So from this relationship, I can immediately conclude from my previous knowledge that this A infinity by V infinity is 1 by Mach number, and this is 1 by Reynolds number. where we are using the fact that S half can be considered to be C by convention. So you clearly now see that the lift is a function of this particular value, which is rho Vs, and then Mach number and Reynolds number. So this is a very important equation we have obtained. We now know that what we started with, the functional relationship, has led essentially to this relationship. So of course this also makes a lot of physical sense. We know that if we are flying an aircraft through air, it's going to depend on the density, because the density is going to produce the lift. It's also going to be related to velocity of the body, and the size of the body, the size of the wing chord, and so on. And also there is going to be some effect of Mach number and Reynolds number, because compressibility effects and viscous effects are going to be important, and these two effects are going to come in through these two numbers. So now let's write this formula again, and let's now look at what we do to define the lift coefficient. So what we are going to do is we are going to write L as this form. So we are going to say L is half rho infinity V infinity square SCL. And to do that, I have to define CL in this form. So essentially CL is used to absorb all the remaining coefficients here. And if you take a good look, you can clearly see this is non-dimensional, because Mach number, Reynolds number were both non-dimensional. And we also had assumed Z is non-dimensional, and of course E and F are non-dimensional numbers. So this is the value of CL here. Now from this equation we cannot just calculate CL, because first of all we do not know what is Z, we do not know what is E and F and so on. But we know that there is some value here, some lift coefficient, which would be expressed in this form. And if I write this equation here, which is essentially same as L is dynamic pressure into the area into CL, then I can write CL is L by Q infinity S. So this gives me a way to calculate the lift coefficient. So essentially lift coefficient could be calculated, for example, by experiment. If I were to take a certain wing or aircraft and put it in a wind tunnel, I could get a lift, I could measure that. I could calculate Q infinity, because I know half rho V square, I know the density of air, I know the velocity of air, and I also have S from the geometry of the body. So essentially I could calculate CL from experiment. Now the same kind of thought process can be used to get the drag coefficient, that is CD, and the moment coefficient, that is CM. So for example, if I were to write the drag would come out as Q infinity SCD. So you exactly follow that same dimensional analysis process and you will get this equation. And also you will get moment is Q infinity SCMC, and this extra C comes in because we are talking about moment here. So it is a force into a distance. So that gives me the moment. So again, if I wanted to find CD and CM, I could do it by experiment, because they are related to the measured drag and the measured moment. And of course I would have chord also, that's a geometric property of the system. So in these equations we essentially have the lift, drag and moment, which are measurable properties of the system. You have Q infinity, which comes from density and velocity, which are coming from properties of the air. And then you have S and C, which are geometric properties of the system, which are essentially the properties of the aircraft or whatever flight vehicle you are working with. So now we again go back to our figure of the airfoil section, which was discussed before. And now we have, for a given airfoil, CL is a function of alpha, Mach number and Reynolds number. CD is a function of alpha, Mach number and Reynolds number. And CM is a function of alpha, Mach number and Reynolds number. So if we keep these Mach number and Reynolds number fixed, then if we vary alpha, we can actually get CL is CL alpha, and later we are going to see that we can plot some of those figures and so on. Now how you would get these values CL, CD and CM? So again, a lot of people did experiments many years ago and they are all tabulated. There is a book on wing sections, I think by Abert and Fondonoff, and you can look at the book for all the different tabulations. For example, for NACA 0012 airfoil. If you go and look there, you will find various tables for that. And also you could get it from some of the modern tools such as computational fluid dynamics and so on. So let's summarize today's class. We saw that there are non-dimensional measures of lift, drag and pitching moment, and these are the coefficients related to each of these forces and moments, and we defined these coefficients. We use some dimensional analysis techniques to get there. We also saw that these coefficients CL, CD and CM are functions of alpha, Mach number and Reynolds number for a given airfoil. And wind tunnel tests and computational fluid dynamics can be used to get all this data as functions or tables. And these are essentially obtained at a variety of points. And then if we are at a particular point in terms of alpha, Reynolds number and Mach number, we can use numerical interpolation to get the precise values of CL, CD and CM. And once we have CL, CD and CM, we can calculate the forces and moments on the airfoil or the wing section. So do remember that if I have CL, CD, CM, then if I can get the dynamic pressure, I can get the wing area, the chord and so on, I can very easily calculate the forces and moments. So in many cases, you have this data available in tables like this. So here I have mentioned CL, CD, CM. You have different angles, you have Mach numbers and Reynolds numbers. And so if you have ever taken a numerical analysis class, you know there are interpolation techniques which can easily be used to find precisely at the alpha you are at the M you are at the Reynolds number you are at, what is the value of CL, CD and CM. And this is often used in many computer programs which are written to generate the values of lift, drag and pitching moment, which are further used to calculate the aerodynamic loads which act on the aircraft, which again then are fed to the structural loading of the system or for performance or flight mechanics purposes. So this was a lecture for today. This is an important lecture because you clearly saw how the CL, CD and CM can be obtained and how it's actually a very good use of the dimensional concept. So I hope you enjoyed this video. I'll see you in a video sometime soon. See you then.